Hi, I'm Sadun Perera.
Hi, I'm Khiren Menon.
I'm Ahsan Saleem. Lab E3, MSI and Sequential Circuits.
Alright, so this is part 1 of Lab E3. This is the schematic diagram with all the pin numbers. This is a state diagram that we drew, and this is the prediction table that we made. And so if you look on the right here, this is the completed circuit. And so like, as you can see from these, the light output over there, it follows the inner diagram, considering that both the switches Ka and Kb are giving a value of 0. So over here it rotates between 111 and 011. However, if both these switches were to give a value of 1, then we would enter the outer loop. So the outer loop 100, 110, 001, 000, 010, 101, 100, and so on and so forth. It would just keep in that outer loop. And once we give them a value of 0, we'll enter back into that inner loop. However, if we were to do so at, for example, 101, there we go, it would lock that value, as can be seen in the state diagram. There's another value as such, and that value is 001. So you get to, there you go. There we go. So 001, if it were to leave enter values 0, K and Kb, then it would lock that value. There's another two things I'd like to mention. So once we enter the inner loop again, so rotating between 111 and 011, at what point in which we enter the outer loop will be reflected within the state diagram as well. So if you were to leave at 011, then we will begin with 100 and then enter 110, 001, 000, and so on and so forth. And if we were to like exit this loop at 111, then we will start with 000, 010, 101, and so on and so forth. Thank you.
Okay, so I'm going to be showing you part 2, circuit 2, in which they ask for a minimum function of these values here, meaning all of these should return a positive value of 1. We'll be using this 8-to-1 multiplexer and a single NAND gate. So over here is the circuit that we've created. So over here, as you can see here, this is the NAND gate that I was speaking about. Basically, this input is just connected to the VCC, whereas this input over here is connected to the D switch. And so basically, this is just the logic is acting as a simple inverter. It's just turning D into not D. 11, 10, and 9 are A, B, and C switches, and number 5 is our output to show our light. And so this is the truth table that we've created. And so as you can see here, all the values asked for, so like 3, 4, 5, 6, 8, 10, 11, 13, 14, all return values of 1, whereas the rest all return values of 0. And so this is a constructed circuit using the 2 chips. And so, for example, like if we look at number 5, it's 0, 1, 0, with the switch turned on, the D switch turned on should return a positive value. So like as you can see, it's turned on here. Number 6, 0, 1, 1 will give you a positive value. So yeah, like this. Number 7 will, with the 3 here, will return negative value, so no light on. Number 8 will give you light on. Number 9, however, will give a light off as a D switch as well. Number 13 will these 3, sorry, will give you a light on. Number 14, these 3 will give you light on. So yeah, thank you.
Alright, so this is part 3 of question 2. This is the demonstrative implementation over here. This is the schematic diagram, and this is the logic table over here. So as you can see, we used the 138 chip and we used the 74HC10 chip here. So just have a look at the logic table. Basically, we're trying to prove what output we get when we give a specific input. So for example here, when an input of 1 is given to B, an output of 1 is obtained. And when inputs 1 are given to B and C, output 0 is obtained. So coming to the logic board here, basically we have provided 3 inputs to the 74HC138 chip, and we have provided 1 output from the 74HC10 chip. So basically, as I had mentioned earlier from the logic table, if I press B, the light lights up. We get an output. However, when we press B and C together, we don't get any output. And also, when we press A and C, we also get an output as the logic table dictates. And when we press A, B and C, all 3 of them, we get no output, which is in accordance with the logic table which I had shown earlier. Thank you.
So this is part 3 of lab 3. As you can see, this is the circuit, this is the key map. As you can see, this is the circuit board. So you can't see any output on the circuit board, but you can see the changes in the oscilloscope. So in the oscilloscope, this part where ABC reaches 111, so there's a drop on the yellow line here, which is called static 1 hazard. So to stop the static 1 hazard, we have to add a redundant gate. So over here, so we have to add a redundant gate over here, and that will stop it. So yeah, this is the solution to reduce the hazard 1, static hazard 1. So we added another gate, so it's a 999 gate. So as you can see here on the board, it's a 999 gate, but we can't see the output. The output can be seen in the oscilloscope, where there is no changes in the yellow line. ABC drops at 1, there's no changes. So that means static 1 is 0. Thank you very much.